We spent the last few days talking about refraction, the bending of light due to the change in speed of a wave when it goes from one medium to another. Today we're going to look at lenses, curved lenses, convex and concave lenses. Lenses that are thicker in the middle than they are at the edges, convex or converging, and lenses that are thinner in the middle than they are at the edges, diverging or concave. Concave, you can think of it as caved in. Concave, caved in, thinner in the middle than they are at the edges. These are good applications of this phenomenon of refraction that we've been talking about for the last couple of days, because lenses are made out of glass or acrylic or plastic or whatever, and they refract light when the light enters them and leaves them. But lenses are designed in such a way to make the amount of refraction predictable and useful. Predictable and useful. Now, we could do Snell's law calculations technically with lenses, but we don't need to, because we have some equations and some methods that are tailored to this specific type of refraction that's taking place. Let's talk a little bit more about these lenses here, all right? These converging or convex lenses are called converging because they tend to converge rays of light. Rays of light that are coming towards the lens tend to come together as opposed to spread apart. Diverging lenses tend to have rays of light that spread apart from each other or diverge, hence the name diverging lenses. Take a look at the diagram up here, the picture up here for the convex or the converging lens. What do you see? What is this? It's a magnifying glass, right? Magnifying glasses, you've all used them before. You know they're thicker in the middle than they are at the edges. You know that they magnify print. But you also take a look at the diagram to the right here, the picture to the right of, who is this? It's Chris Hadfield. It's Chris Hadfield. He tweeted this photo when he was in space in the International Space Station of a water droplet just hovering in front of him. Why, just as a little aside here right now, why is that water droplet not teardrop shaped like they are on Earth? Yeah, because you've got these internal forces, these internal cohesive forces that are keeping the water droplet together, and it's nice and uniform. So it produces essentially a perfect sphere, but as soon as you have gravity acting on it, it drags down on the bottom of it and creates this teardrop shape that we don't have there. This serves as a convex lens. This water droplet is thicker in the middle than it is at the edges. But you notice we get a completely different image formed here than we do right here. Here, the image is magnified, right? We produce an image that is right side up and bigger. But here we produce an image that is, if you take a look inside that lens or the water droplet, it's upside down and smaller. But yet it's with the same thing, with a convex lens. We're going to learn today how to figure out what the image is going to look like, how to predict what image we're going to get, bigger, smaller, right side up, or upside down, or whatever the case may be. The bottom ones, the diverging, the concave, the ones that are caved in or thinner in the middle. Okay, the best example that I can give you of that is of eyeglasses. Okay, I have diverging lenses as my eyeglasses. I would bet that you do too. I would bet that you do, okay, that you do, you don't. Okay, you have converging ones. Okay, you have diverging ones. Okay, I can tell you have diverging. Almost everybody, almost all young people that need glasses have diverging lenses. Not all, but most. If you don't need diverging lenses now, it is quite likely that you never will. If you don't have converging now, you will likely need them at some point in your life. Presuming you live long enough, you will likely need them at some point in your life. For you and you and you and you and me, we're going to need bifocals. Okay, that's the reality of it. When we get older, we're all going to need bifocals. I'm close to needing bifocals now. Okay, in another 30 years, you're probably going to need bifocals as well. What happens is that I am what we call nearsighted. that means I can see near. I am nearsighted. I can see near. I can't see far away. And that's because the rays of light that are coming into the convex lens in my eye are converging, right? Converging, convex. They're converging in front of, what's this called? They're converging in front of the retina of my eye. They're supposed to converge on the retina of my eye. By the time those rays actually make it to my retina, and they do, but they're not converging there. They're kind of spread out a little bit, so it produces a fuzzy image, an unfocused image. The idea here now is that I stick a diverging lens in front of my eye, which causes the rays to spread apart a little bit, to diverge, and then they converge to the right place, right on the retina of my eye. If this happens, it tends to happen in younger people because our eyes are basically a little bit too long. And the rays converge a little bit too soon for the length of our eyeball. That's not going to, if you don't need it yet, it's not likely going to change for you. Okay, you're not going to all of a sudden stop being able to see things that are far away. But if you are farsighted, yeah. If you can see far off, okay, which you can. If you can see far off, then it is quite likely that the muscles in your eyes will weaken over time to prevent you from being able to see things that are far off. You'll lose that ability to see far off. And what's going to happen in that case is that the rays of light that are coming through your lenses of your eyes are going to converge, but they're going to converge together behind your retina. So you're going to need converging lenses to bend them a little bit more before they go into your eye. Does that make sense? We call it myopia. The technical terms are myopia and hyperopia. Myopia is when, this is the way I remember it, myopia is my vision. I can see nearby. I can't see far off. Hyperopia is the opposite. At some point, I'm going to be myopic and hyperopic as well. I'm not going to be able to see either one, and that's why I'm going to need both convex and concave lenses in order to see it. Okay? Carly's got glasses right now. The good news is for Carly is that she probably will not ever need bifocals because she's got the convex lenses right now. Okay? The bad news is for me, I've got concave lenses right now. I will need convex lenses. So your eyes may or may not get worse as far as, is that right? As far as the ability to see nearby things, but you're probably not going to lose the ability to see far off things. Okay, I will lose the ability to see nearby things, as will you and you and you and everybody else in the room. All right. All right, what kind of lens is this? This is convex, or what's another name for convex? Converging. We did a little demonstration a minute ago with the Canada flag and the rays of light coming through a convex or converging lens. We found that all rays of light parallel to, what did we call this line a minute ago? The principal axis. All rays of light parallel to the principal axis will converge at a point that we call the focal point. This is the focal point of this lens. This is the object. This object is going to be Mr. Aiello. You'll see why in a minute. Mr. Aiello is our object. There's a focal point on the other side of this converging lens. This we're going to call 2F. Not because it has any optical significance other than as a spacer. Rays of light don't go through 2F. Rays of light go through F. But we're going to use that as a spacer. I'm not even going to label those dots on the other side, but this would be the same distance as F, and this would be the same distance as 2F. Just remember that the real focal point is on the right-hand side, and 2F would therefore be on the right-hand side as well. There are millions of rays of light reflecting off of Mr. Aiello. Millions of rays of light. Almost an infinite number of rays of light reflecting off of Mr. Aiello. They all go one way or another. Probably hundreds of thousands or millions of them are actually going to reflect off of him and go through this lens and refract. We could, through a series of Snell's law calculations, determine exactly where those rays went, all of them. But there are two rays that are particularly predictable. So we're not going to do these Snell's law calculations here. We're going to draw two rays that are predictable, and that's going to determine for us what the image of Mr. Aiello is going to look like. Right? When I look at a newspaper through a magnifying glass, what does the image of the newspaper look like? When I looked at that Canada flag through that convex lens, what did the image of that Canada flag look like? Okay, so here, what does the image of Mr. Aiello look like when his object distance, that's this distance right here, is greater than 2f, which is this distance right here. Well, let's draw those two rays, those two very predictable rays. Remember, millions of them, we could draw a million of them, and we could do some calculations for all of them and figure out where the rays went, but these two are very predictable without the need to do our Snell's law calculations. So that's what we're going to do. First ray of light is going to reflect off of Mr. Aiello's head. Why do we pick Mr. Aiello? Well, it's a little bit easier for light to reflect off of his head than it is to reflect off of some people's heads. So this ray of light reflects off of his head parallel to the principal axis. Why this one? Well, because we know that this ray of light will refract down through the focal point. All rays of light parallel to the principal axis refract through the focal point. Now, I've got to let you in on a little secret here. I've drawn this technically wrong. It works. The effect is exactly the same as if I draw it correctly. But it's easier, slightly easier the way that I've drawn it. Technically what happens is when the light strikes this lens, it bends, and then when it leaves the lens, it bends again. So we get two refractions there instead of one, right? But the end result is that it comes out here. So it's easier just to draw it like the way that I've drawn it here. Now there's a million other rays that I could draw. I'm going to pick one because it's very predictable what happens to that one other ray as well. I'm going to draw that one also from the top of Mr. Aiello's head. So sunlight reflecting off of his head. It's going to go down through a point that we call the optical center. And it just goes straight through. Not really straight through. It bends and then it bends again, but the net effect is if it goes straight through. The top of the object, or the top of Mr. Aiello's head, is where the rays started. The top of the image is where the rays come together. This red arrow represents not Mr. Aiello. This is Mr. Aiello. This red arrow represents the image of Mr. Aiello that I've just produced from this lens. There are three characteristics of the image of Mr. Aiello. One relates to the size. The image is smaller than the object. Mr. Aiello, right here, appears to be smaller than he actually is. The image is smaller than the object. The object started at the principal axis, ended where the rays started. The image starts at the principal axis and ends where the rays converge. That makes the image upside down or inverted. Now the next one, you're not going to completely understand this one yet. You're just going to have to trust me for a few minutes on this one. We're going to say that this is a real image as opposed to a virtual image. That's the other kind, a virtual image. A real image is an image that can be projected onto a screen. Like when I did the demonstration with the Canada flag, the image of that flag was projected onto a screen. If it's a virtual image, you can't project it onto a screen. You got to physically look in the lens to see it. If I use this as a magnifying glass, I can't project the image of that paper onto a screen. I have to look through the lens to see it. That's a virtual image. The first demonstration I did was a real image. On a screen, real, got to look through the lens, it's virtual. Now, how do you know when it's real and how do you know when it's virtual? We'll talk about that in a few minutes. Let's draw the next one. This time, we're going to say DO is equal to 2 times F, right? Focal length, 2 times the focal length, and then on the other side, my object distance would be the same as 2F. Once again, Mr. Ello's particularly efficient light reflecting head reflects an array of light from the top of his head parallel to the principal axis. It will go down through the focal point. Next ray from the top of Mr. Ellis' head down through the optical center. It should form an image right here, directly below 2F. It is. How does the size of that image compare to the size of that object? What is it, Nick? Yeah, it's equal, same size. Look at the size of this red line, the image of Mr. Allo, the size of the black line, the object, Mr. Allo, the real Mr. Allo. It's the same size. Is it right side up or upside down? Yeah, it's upside down. Mr. Allo is still upside down, right? We'll say inverted. You use the term upside down. I don't really care. I don't really care what term you use for, as long as it describes that it's not right side up. Real or virtual? Trust me, it's real. I could project this onto a screen if I wanted to. I don't have to. Like if I don't have a screen here, if there's no screen there, there's still a real image. It just means that we can project it onto a screen if we want to, if we chose to. Next one. Okay, next one. This time our object distance is greater than F, right? But yet it's smaller than 2F. So we're going to say DO is in between 2F and F. First ray is going to go from the top of Mr. Ellis' head, parallel to the principal axis, and it's going to go down through the focal point. Second ray is going to go down from the top of Mr. Ellis' head through the optical center, and it's going to go straight through. Look at what the image form looks like this time. This time the image is larger, smaller, same size. Look at the red line compared to the black line. Is it bigger? It's bigger. It's larger. What about right side up or upside down? Mr. Allo appears to be upside down. He really isn't, right? He's really right side up, but his image is upside down or inverted. And real or virtual, trust me, it's a real image. If I choose to, I can project the image of Mr. Allo here onto a screen. So we went from, like when the object was really far out, an image that was smaller and upside down. Then when it got closer, it was same size and upside down. And now it's bigger and upside down. This is a projector, right? Like, look at this. This is literally the lens for a projector. You're staring at it right now. The image that you see right now is larger, smaller, same size. Like, where does the object come from? Inside there. How big is the image compared to the object? Bigger, right? Oh, but wait, it's right side up. Look at the projector. It's upside down. So the image is still inverted here, right? Now, You could flip that projector over and still make it work. There would be a button to electronically flip the object over. Bottom line is the object inside the projector always has to be opposite to the way that you want to view it. And it's real. It's being projected onto a screen. It's real. It's inverted compared to what the object is, and it's larger than the object is inside that LCD projector. Have a look at this one. This was the wacky one. This time our object distance is exactly equal to the focal length. First ray, parallel to the principal axis from Mr. Ellis' head down through the focal point, because all rays parallel to the principal axis go down through the focal point. And then the second ray is going to go down through the optical center. What do you notice about these two rays on the right-hand side? They're parallel. They don't converge. Let's extend them backwards for a second with dotted lines. Well, they're parallel. They still don't converge when I extend them back like this, right? What do you say about that image? There is none. If the focal length of this lens is 15 centimeters, and I put a newspaper 15 centimeters away from it, I won't see an image. It's not that light's not going to go through. It is. Light is going to go through the lens, but it's not going to focus, and you're not going to see an image of the newsprint anywhere. There's no characteristics if there is no image formed. Remember, light always goes through, but light going through doesn't form an image. Light going through causes a blur unless the light focuses. Next one. This time, man, look, this time the object is like really far in. Mr. Aiello is really, really close to the lens. He's closer than the focal length. DO is smaller than F. Let's draw those rays of light shining off of Mr. Aiello's head here. First ray comes off his head, parallel to the principal axis, and it goes down through. Let's try that again. It goes down through the focal point. Second ray goes from top of Mr. Aiello's head down through the optical center. Hey, do those converge over there? No. So let's extend them. Let's extend them back. Hey, they converge over there on the left-hand side, don't they? Let's draw the image of Mr. Aiello over here. What are the attributes or the characteristics of Mr. Aiello's image this time? Larger, smaller, same size? Larger. He appears to be larger than he really is. It's a magnifying glass, right? You look at something through a magnifying glass, it appears to be larger. You have to have an object that is close to the magnifying glass to make that work, though, right? Not far away. Larger. It is right side up or upside down? Right side up, or we'll say upright. I don't care what term you use to describe that, as long as it, bless you, as long as it tells you that it's right side up. Real or virtual? This is virtual. For the first time, we see a virtual image. Now, listen very carefully. Real image can be projected onto a screen. Virtual image can't be projected onto a screen. We know this because back here for a real image, solid lines intersected. And here for the virtual image, dotted lines intersect. Does that make sense? Real image is formed when it can be projected onto a screen, and we know that it's real because solid lines intersect. Virtual image cannot be projected onto a screen. We know that happens when dotted lines or the extensions of those rays intersect. Okay, I got one more to draw. This time, what kind of lens we got? This is concave. This is diverging. We still call this, by the way, the principal axis. This we're going to call F. This we're going to call 2F. I'm not even drawing F and 2F on the other side. Notice this time, though, that F and 2F are on the same side as the object. So remember this last one, here's our object right here, and our focal point is on the other side. This time, here's our object, and the focal point is on the same side. Call that a virtual focal point. We'll deal with that more tomorrow. I'm only going to draw this first diagram for you, and then you're going to draw the last four yourself. The first ray that we're going to look at is going to reflect off of Mr. Ayla's head. It's going to hit the lens, and it's going to refract. Where's it going to refract? I'm going to give you four options. Option 1. How many people say yes? Nope. Option 2. How many people say yes? Option 3. Option 4. The answer is option 4. It refracts away from the focal point. What do we call this lens? It's a concave, or what is it? Diverging. The rays diverge away from the focal point. Now, let's extend that back. It's easier for you guys to do because you got a ruler. Make sure your ruler touches this point, and then just draw the line, right? Some of it's solid, some of it dotted. Next ray, well, it's going to go through the optical center, and it's going to keep going straight through like it did with the converging lenses, just like this. These rays converge, right? We got an image formed right here. What are the attributes of that image? Larger, smaller, same size? Smaller. The image is clearly going to be smaller than the object here. Is it right side up or upside down? It's right side up. It's upright. Is it real or virtual? Yeah, it is virtual, yeah. Its dotted lines intersect. It looks like only one dotted line intersects here, but you know what? It's fine to draw like this, but strictly speaking, if we, Colton, look up here. If we extend this one back, we can see that really it is two dotted lines intersecting, right? So you were right. It is a virtual image because two dotted lines intersect. We just don't usually draw the second dotted line, that's all. We will say that it is a virtual image. You're going to find when you draw the last four ray diagrams here, no matter where you put the object for a diverging lens, the image will always be smaller, it'll always be upright, and it'll always be virtual. Now, it may move around a little bit in here. It may get a little bit bigger than it is right now, but it's always going to be smaller than the object. It's always going to be right side up, and it's always going to be virtual. Okay, that's what I'm leaving you with. Those last four ray diagrams. Good news is you draw them almost identical to the way that you draw this one. It's easier than with the converging lenses because that changes depending upon where the object is placed. These ones don't.